Very good. So our next speaker, Nina Balcan, is a colleague of mine at Carnegie Mellon University. She has been doing machine learning since before machine learning was fashionable, or before it was as fashionable as it is now. Last night she told me that in 2017 she actually was one of the organizers of a special semester here at the Simon Institute on machine learning.
First one, machine learning assignments.
The first one in machine learning assignments. But then you couldn't attend because your son was born.
My daughter, yeah.
Your daughter. Okay, so anyhow, we're delighted now that she is able to be with us, and she'll talk to us about machine learning for algorithm design.
Okay, cool. Thank you, Jeremy. So, so my talk today will be about machine learning for algorithm design, and I guess this is a broader audience. I guess people from math, computer science. I'm going to start at a very high level. So at a very high level, I'll talk about topics at the intersection between machine learning, of course, we all know a branch of AI, a highly successful branch of AI, and algorithm design. This is a topic studied in many different fields, including, of course, theory of computing. And in the first part of the talk, I will talk about machine learning for algorithm design, and in particular about, I think, an exciting recent direction for designing and analyzing data-driven algorithms. And here my focus in this part of the talk will be on telling you about what kind of provable guarantees we can prove for these data-driven algorithms. So this is a topic that I've been working on in my group in the past decade. And so the exciting thing here, we have provable data-driven algorithm design techniques. Okay, and so that's the first part of the talk. And then in the second part of the talk, I will also show how we can actually loop back and talk about machine learning algorithms themselves. And so, and more specifically, to be concrete, we can talk about provable hyperparameter tuning of machine learning algorithms, which is, of course, because machine learning algorithms themselves have hyperparameters, and can we do that can we tune them in an efficient and provable way? Of course, this can be very impactful, because these days hyperparameter tuning is done with a lot of human and computational effort. So if they can do it in a more intelligent way, it can be incredibly important. Okay, so these are the two parts of my talk, and so I'll start by talking. So feel free to ask any questions at any moment in time. So I'll start by talking about the first part. Okay, so the first part is about machine learning for algorithm design, and again, because this is a very broad audience, just very briefly, what is an algorithm? Well, it's a finite sequence of precise step-by-step instructions to solve a well-specified class of problems. And again, to be concrete, for now, let's think about algorithms for solving discrete or combinatorial optimization problems, where maybe the inputs or the outputs or both might be combinatorial. Okay, so for example, we might want to think about clustering, where the goal is, if we're given a set of input items, we want to somehow organize them into natural groups. Okay, or we might think about the problem of pricing a given set of items in order to maximize revenue. Or we might think about a subset selection problem, where the goal is to output the most valuable subset of items subject to some capacity constraints. Okay, so these are just examples, but more generally, let's think about algorithms for solving combinatorial problems. And now, let's reflect a little bit. So what is a classic approach in theory of computing for designing and analyzing algorithms for such problems? Okay, so the classic approach goes like this. We fix the problem that we want to solve, and then we have a genius scientist, maybe Venkat, that sits down, or maybe Prasad, or Jeremy. So sits down, our genius scientist sits down, has a stroke of genius, and then hand designs an algorithm. So by hand designs an algorithm, and then from an analysis point of view, what our genius scientist is thinking about, he's thinking about worst case analysis. So how well is our algorithm doing on a one-shot worst case instance of the underlying algorithmic problem? Okay, so the classic way to analyze and design algorithms in theory of computing thinks about hand-designed algorithms, and from guarantees point of view, we consider worst-case analysis. Now, when it's possible to hand-design algorithms that have good worst-case guarantees, that's fantastic, right? But unfortunately, for many problems, including problems that I listed here, a lot of the hand-designed algorithms come with weak performance guarantees. And so in practice, rather than using hand design algorithms that have weak worst case performance guarantees, what practitioners have been doing more and more is to try to incorporate machine learning into algorithm design. Okay, and of course, this makes a lot of sense. By the way, not only because machine learning is so hot, machine learning and AI are very hot these days, so this makes sense not only because of that, but actually it makes a lot of sense because often in practice, we need to solve not only one instance of the underlying algorithmic problem, but we need to repeatedly solve instances of the underlying algorithmic problem that come from our domain. So there is really an opportunity to try to use machine learning and past instances of the same underlying algorithmic problem to learn an algorithm that does all on our type of instances, on our domain, rather than worrying about worst case instances. Okay, and so actually this idea makes a lot of sense if you think about it, and people have looked at it in the research community starting around 2000 in several different more applied fields, like in fact AI, for problems like SAT solving, computational biology, and game theory. And of course, there is an explosion of interest in recent years. But of course, so this is on more applied work, but until very recently, basically, there are no provable guarantees for these data-driven algorithms, right? Because the beauty of the classic algorithm design and analysis in theory of computing is that they come up with provable guarantees. So the question is, can we also, what kind of provable guarantees can we provide for now these machine learned or data-driven algorithms? Is it possible to provide any interesting provable guarantees? Okay, and this is a topic that we've been working on with my group, with my students and postdocs for a few years now, and this is what I'm going to tell you a little bit about today. And so we had a variety of case studies and sort of general principles, and I'm going to share you some of those with you today. Okay, and before going a little bit, because at some point I'm going to try to be a little bit precise about how do we formalize the problem of data-driven algorithm design as a machine learning problem, first I want to stay a little bit at a high level, just to give you a flavor of the type of guarantees you can hope to even consider. Okay, so first, one direction that we have been exploring is analyzing algorithm design as a statistical learning or distributional machine learning problem. Here, basically, we fix the problem that we want to solve. We fix a large parametric family of algorithms for our problem, that has our favorite algorithmic kind of components, maybe dynamic programming, greedy, and so on. It could be also that, so we fix the problem that we want to solve. We fix a large family of algorithms that has kind of algorithm components of the type that we are used with. Maybe some of these components might have even also real valued knobs that one can hope to tune, so maybe this family is infinite. Okay, and so then what we do, we take a sample of typical instances coming from our domain. So for example, if we are doing clustering, we take, this is how the typical instances might be looking like. This might be input number 1, a graph, input number 2, a graph, and so on, input number m, another graph. So these are examples of typical past instances for my problem. Or if I'm doing, so this is for clustering, or if I'm doing pricing, the inputs might be just, for example, an input 1 might be if I have a number of customers, what is their values for various subset of the items, and that this will be one input, and so on, and I'll have several of them, like maybe m such inputs, right? So we fix the problem that we want to solve. We then assume that we have access to a set of typical instances for my problem, and as we'll see when I discuss it formally later, we'll assume that these typical instances are drawn IID from a fixed unknown distribution of our typical instances. But of course, based on such typical instances, our goal is to come up with an algorithm from this large parametric family of algorithms that does all our new instances that come from the same domain, right? That's what we want to achieve. And so this brings a very important question, what we call in machine learning theory, a sample complexity question, okay, which asks kind of how large should the set of typical instances be in order to guarantee that if we learn an algorithm that does well over the past training set of typical instances, that the algorithm will do well on instances that come from the same domain. Okay, so this is a key question that we'll have to think about. And again, I'll come to this more, I'll talk about this more formally later, but first, for now at the high level, the cool thing is that actually we can, at a high level, build on tools from statistical learning theory to answer this question. And so, for example, we know from statistical learning theory that the number of samples that we need in order to generalize, the number of samples we need to generalize depends on how intrinsically complex a certain family of functions is. This is a family of functions induced by my family of algorithms and my performance measure at hand. Okay, this family of functions is very complex in a learning theoretic sense, and I need more samples to generalize. Okay, so it turns out we can build onto statistical learning theory, but the challenging fact is, that we are learning more complex objects. We are learning algorithms, not classifiers. So that's why there is a lot of cool theory that has to be developed to analyze data-driven algorithms, even in statistical settings. Okay, so I'll tell you about this more formally in a few minutes. Okay, so that's one way to think about algorithm design or data-driven algorithm design as a machine learning problem. There is also another way to think about it. For example, you can use kind of the online learning formalism. So in the previous formalization, I assumed that all the instances, training instances, past instances of the problem are all given up front to me, and they're all IID. Okay, but what if the instances arrive online one by one and they are not IID? So that's why we can also do online algorithm selection as a formalization. So here what we do, maybe we are still trying to solve some clustering problems, for example. And so what we can do, what we have to do here each day, maybe, or in each round before the new data set arrives, I have to pick an algorithm, maybe algorithm A1. And then a new instance of the problem is revealed, a new instance of the clustering problem is revealed. I apply my algorithm A1 on this instance of the problem, and then I see how well, maybe I'm applying my algorithm A1 to cluster this data set, and then, I see how well I'm doing, right? I see how well did my algorithm perform on this instance, and maybe I can also measure how well other algorithms would have performed on that instance. Okay, and based on this information, the next day, again, before I see the new instance, I have to select a new algorithm to run, and then I get another input, say input 2. I run my new algorithm A2 on this instance. I output a clustering, which is what my algorithmic task was, and then again, I measure how well I've done on this instance. So I get feedback, basically. In learning theory terms, or machine learning terms, I get feedback. And based on this feedback from this round and the previous rounds, in the next round, again, I have to select an algorithm. Then I get a new instance of the problem. And again, I see how well my algorithm that I selected does, and so on. And I keep doing this. And now you might ask, the question is, what guarantees do I want? So, for example, a type of guarantee I might want for my online algorithm selection procedure is to achieve no regret. So in plain words, what no regret means that we want to make sure that our cumulative performance over the history of my learning procedure, algorithm selection procedure, is comparable to the performance of the best fixed algorithm from the family in hindsight. So I have no regret compared to the best fixed algorithm in hindsight. Okay, so that's an example of a guarantee I might want to provide in this online algorithm selection scenario. Okay, and actually, I phrased data-driven algorithm design both as a statistical learning theory problem and as an online learning theory problem. So, and the question is, what's new here from machine learning? Can we just apply existing machine learning tools? And the answer, no. Actually, we are learning much more complex subjects. We are learning algorithms. The induced loss functions are very volatile. And so we really had to develop new tools. That's the major challenge, actually. So the induced loss functions, you'll see in the rest of the talk. If I fix an instance of the problem and vary the algorithms, I might get many sharp transition boundaries in terms of how the performance function behaves. And so that's very challenging, and so we really had to develop new tools in order to analyze, to give no regret guarantees in the online scenario, or to give statistical guarantees, sample complexity guarantees, a distributional learning scenario for these data-driven algorithms. So it's also very exciting from a learning theory point of view, not only from an algorithm design point of view. Okay, and so what I'm going to do right now, I'm going to tell you a little bit about, a little bit more concretely about some type of results we can get for these problems, and some implications, and then towards the end of my talk, as I mentioned, as I promised, I'll go back to machine learning itself, and I'll talk about learning machine learning algorithms. Yep.
So when you see a new problem, you're allowed to run like several of the algorithms that you're selecting from it, or just one?
Yeah, so there are various formalizations, ideally just one. But you could also consider, in my talk, I'm going to consider on a new instance of the problem, I'm just going to run one of them. Because I could always run many of them and pick the best, but I don't want to do that. Maybe at the test time, I just want to run one algorithm.
So I guess I'm confused about the no regret part, because like a priori you don't know which one is the best, right?
The best in hindsight over all instances, right? So that's non-trivial. I agree with you. It's not obvious why can you even get this guarantee, but turns out you can. And I'll mention a little bit about it. Yeah. So it's like, because I guess what the guarantee is, again, like no regret means we want to come, so our cumulative performance, so we run, so it's not instance by instance, but if we look back, so if I go back to my picture here, so maybe if I'm here and I look back in hindsight, how well did I done, how well I've done when I run algorithm A1 on instance 1, algorithm A2 on instance 2, and so on, algorithm M on instance M. If I sum up my utility function, the utility that I've got over my history, that has to be close to the utility of the best single fixed algorithm in hindsight. So it's no regret, it's called no external regret. I compete with the best expert, the best fixed algorithm in hindsight. There are generalizations of this, and so, it's not entirely obvious that you can even achieve this. But in learning theory, people know that you can achieve this. For example, if the loss functions are convex, there is a long history that connects also with optimization and learning theory. Basically, it's not obvious that even if the loss functions are nice, you can get no regret. But then for that, there exists cool work in learning theory and optimization. What's exciting here for us to also show that you can get no regret, even if our loss functions are very challenging. They'll have many sharp transition boundaries. Yeah?
So if you treat each algorithm as an expert and just do one of the standard online regret minimization algorithms, like follow the...
Yeah, if you have a finite number of, I'll come back to this. If you have a finite number of algorithms, yes, you can do that, obviously. Right. But we are considered parametric infinite families of algorithms. And then the issue is, again, actually, if basically, my experts are maybe these algorithms parameterized by real values, for example. Here, the issue is that if I fix, for instance, the problem and vary the hyperparameters, for example, for the clustering problem, if I slightly change the hyperparameter, sometimes you might get a completely different clusterings that induce a completely different utility function. So that's very challenging when you do online learning. In fact, in the worst case, you prove no regret is not even possible once you have sharp transition boundary. That's actually one of the major challenges you even have to overcome. So it's very non-trivial. So, but that is cool. Yeah. Any more questions? Cool. If no more questions, now I can go and talk a little bit more precisely about this, because so far I talked at a high level. So just to make sure we're all on the same page. So I'm going to start by talking, actually, I'm going to talk mostly details about the statistical or the distribution learning formalization. I'm going to mention our results for online learning. Feel free to catch me offline. I can tell you more about those. But starting with statistical learning formalization, actually, this formalization was actually introduced by Rishi Gupta and Tim Ravgarden in an ITCS 2016 paper, and it goes as follows. So we first fix an algorithmic problem that we want to solve, maybe clustering, subset selection, your favorite problem. And then what we do, I'm going to denote by pi the set of problem instances for my problem. And I'm also going to then fix an algorithms family. I'm going to call it alg. It's a family of algorithms, and it's parameterized by a subset P of RD. So it's an infinite family of algorithms parameterized by a subset P of RD. So for any parameter alpha in my parameter set P, I'm going to have an algorithm A alpha in my family of algorithms, right, that I could use. And so then I'm also going to fix a utility function for the given algorithmic problem. So, this utility function looks like this. It goes from the set of problem instances and the set of the parameter set to the bound interval 0h. And so what does it mean? So U of I and alpha measures the performance of my algorithm A alpha on a problem instance I. Okay? And then so I have this utility function again, which U of I and alpha measures the performance of algorithm A alpha on a problem instance I. And then, once I have this utility function, then immediately I also get this family of utility functions, U alpha. So for any parameter alpha, I'm going to have utility function U alpha that goes from the set of problem instances again to the bounded interval 0h. And so it's a family of utility functions induced by algorithm A alpha, by a fixed algorithm A alpha. And so what is U alpha of I? U subscript alpha of I is just the utility that I get by running algorithm I on instance alpha. Very natural. Okay. And just to give an example, a concrete example, because I have not yet given an example of an algorithm. I was assuming that you have all seen an algorithm before. So this is an example from Tim's original paper. So you have an abstract problem, so the classic problem. So so the input here, so we have as an input a set I of n items. And each item I has a value vi and a size si. And we also have a knapsack capacity c. And then our goal is to output the most valuable subset B of items. So we want to output basically the most valuable subset of items that fits in the knapsack. That's in plain words. Mathematically, we want to find the subset B of the set I in order to maximize the value of the items we collect, subject to making sure that these items fit in the knapsack. Okay, and here is an example. So this is my problem. Here is an example of a family of algorithms you might consider for this problem. So this is a family of greedy algorithms parameterized by a set by the real line, right? So what are these algorithms? For every real value parameter alpha, I'm going to have an algorithm A alpha. And what is the algorithm A alpha doing? First of all, I'm going to set a score for each item I, and this score is going to be Vi over Si to the power of alpha. Okay, and then what I'm going to do, it's a greedy algorithm in decreasing order of the score. I'm going to add each item to the knapsack if there is enough capacity left. Okay, so that's in decreasing order of the score, of course. Yeah, so that's a family of algorithms. And of course, different alpha lead to a different output on any input instance. Okay, and now what's the utility function that I'm going to consider? Well, very naturally, the utility that I'm going to consider here, the utility of an algorithm A alpha on instance I will be the value of the items, chosen by the algorithm parameterized by alpha on the given instance I. And the number of items is fixed, yeah. Our bounds will depend on, on how many samples we need to generalize, will depend on the maximum size on the instance, will depend on n. Okay, so that's a concrete example of an algorithmic problem, a concrete example of a family of algorithms, a concrete example of a utility function we might consider for each of our algorithms. And so, as I mentioned, we are studying data-driven algorithms, and we want to learn algorithms that do well on a specific domain rather than worrying about worst-case instances. Now, in this formalization, how do you model the specific domain? We're going to assume, so it's a statistical learning formalization, so we're going to assume that there is an unknown, fixed but unknown distribution over problem instances. And so, and what the learning algorithm can do, can use M instances, I1, I2, IM, drawn IID from this distribution over problem instances. And of course, we can also assume that we can measure the utility of any algorithm A alpha in the family on each of these training instances. So the algorithm is going to use this IID training instances drawn from this fixed unknown distribution over instances. And then our goal will be to find an algorithm from this large parametric family of algorithms that does well on new future instances that come from the same distribution over problem instances as a training set of problem instances. So we want to find an algorithm that generalizes this, that does well on instances that come from the same distribution. Okay, and more concretely, to be precise mathematically, what we want to do, we want to output an algorithm from our large parametric family of algorithms that performs as well as an optimal algorithm A alpha star from this family. And what optimal algorithm A alpha star for the distribution D is one that maximizes the expected utility when I draw an instance at random from the distribution. So A alpha star maximizes the expected utility, this expected utility over all algorithms in my family. And our goal is to output an algorithm based on training instances of problem instances coming from this distribution. Our goal is to output an algorithm that competes with, does nearly as well as this algorithm, optimal algorithm A alpha star. Okay, and now, if this is our goal, especially if you have seen machine learning, but even if you have not seen machine learning, is the most natural thing you could try to do. What should we do? Well, we're gonna find an algorithm A hat that does well over the training set of typical instances. What else would you do, right? Maybe it's the optimal algorithm over the training set of typical instances, or maybe one that is close to the optimal algorithm over the actual training instances that we have. And of course, this brings up, as I mentioned earlier, a very important question, a sample complexity question, right? So because, of course, if our training set of typical instances is very small, we cannot hope to generalize. But as we see more and more training instances coming from the same distribution, we can hope to generalize. A very important question here is this sample complexity question, which asks how large should the training set of typical instances be in order to guarantee that if I find algorithms, maybe I find an algorithm A hat that does well over the training set of typical instances, this algorithm A hat will generalize, will do well on new instances as well, and more specifically will compete with the best algorithm A alpha star with respect to this fixed unknown distribution over problem instances. Okay, so that's precisely what the sample complexity questions are asking. And now, at this level of generality, we can still build on tools from machine learning theory. And so, for example, we know from a machine learning theory that if the number of, or empirical processes from the 70s really, but if the number of training instances that we see in the training phase is large enough compared to the intrinsic complexity of the family of functions at hand, and what's the family of functions? The family of utility functions induced by my algorithms, right? So if the number of training instances is large enough compared to this intrinsic complexity of the family of functions, of utility functions at hand, then that's sufficient to get what we call uniform convergence. And so what are uniform convergence guarantees? Well, are guarantees of the form that I have here on the slides, which tell me how large the training set of typical instances be, so that I can guarantee that with high probability over the draw of the training set of typical instances, I have it uniformly for all the algorithms in my family of algorithms, where performance, average performance over the training set of typical instances is close, say epsilon close to their expected performance on a new random instance. Okay, and so if you think about it, once we had enough samples to get these uniform convergence guarantees here, then it implies that it's enough to show that the best algorithm A hat over the trained set of typical instances will compete with the best algorithm A alpha star from the family of algorithms with respect to the underlying distribution. So uniform convergence suffices basically to get what we want. Okay, and yeah, there's a question. Yeah.
Can you explain why the width of the distribution isn't in the sample size? Why do you not need to know the width or the messiness of your distribution?
So that's the magic of empirical processes and statistical learning theory. So these results hold no matter what the fixed underlying distribution is. Actually, I think that this has beautiful results. They come from Vapnik and Chervonenkis. I didn't yet define what the notion of dimension is. I will define it soon to make concrete. But that's actually the beauty of those results. So turns out that, all you need to know that there's a fixed unknown distribution, and it suffices to make sure that the training instances and the test instances come from the same distribution. And then you get bounds that hold, like you can get these cool uniform convergence bounds that hold no matter what the fixed underlying distribution is, as long as it's fixed and unknown. Now, these bounds depend on this notion of dimension. And they might work no matter what the underlying distribution of a problem instance is. So that's their strength. Now, of course, if you have a very nice distribution, these bounds are not going to capture it because they are kind of worst-case bounds. If you want to do something that is more distribution dependent, you want to use something like Rademacher complexity. There are learning theory results for like Rademacher complexity or NLDC entropy, where they take into account the niceness of the distribution.
Thank you.
Yeah.
This might be a dumb question because I'm seeing some of this for the first time, but the utility function of A alpha is value divided by sample size to the alpha, right? Was that what you mentioned a couple of slides back?
No. It's the utility. You can define. No, the utility. I just defined what's the utility on any given instance. What do you mean exactly? So.
A couple of slides back, you defined. Yes.
So the utility is just the value of the items. So it's just here. It's like the quality of the. For any subset that I pick, is the quality of the subset. And how do I define the quality? The subset is the value that I get, because each item has a value, and this is an example of how I define the utility function for this problem.
Right. So you mentioned that the score of item I is value over sample size to the alpha.
Yeah.
Right. So won't that always be maximized for alpha equals 0?
Scoring utility of the function.
Okay, maybe I'm confusing some basic definition.
You also need to fit in the knapsack. So maybe the item with the largest value might not fit in the knapsack, because also size is important.
As in my question is that it seems like for alpha equals 0, you'll the score will be maximized for alpha equals 0, but maybe I'm mixing
The
up
score
two
is the
things.
utility method maximize the score.
Okay.
The score is something, and the score is just determines the algorithm, but you're not trying to do
I'm not trying to maximize the score. Okay, I see.
So what do you mean the score? So in any case, SI is different from the, so like SI here, so if, for example, in this concrete example, so for this knapsack problem, if alpha equals 0, this will be 1. And so if you pick, this might not be the best algorithm because the item with the largest value might not fit in the knapsack.
Right. I understand.
And so maybe you might, if you use a different alpha here, you might, basically, here you might get the empty solution if alpha equals 0, but if alpha equals n, you might get actually a solution that has some non-zero value.
Right, okay, thank you.
Yeah, but this is just an example, by the way. This is just an example of a utility function for some other problems. For example, we had many case studies. So for those of you that are people in the room, like it can also be like, for example, one of the case studies was learning to solve mixed integer programs via branch and bound, and the solution quality, the utility function, we have a variety of them.
Are you assuming
finite variance?
Am I assuming what?
Finite variance for the distribution?
I don't need that. That's the beautiful aspect. Wow. So you should, if you've never seen these uniform convergence results, definitely look at them. They actually come from empirical processes. Yeah. So like that you hold no matter what the underlying distribution is. But again, I didn't tell you what this notional dimension is. So let me tell you what this notional dimension is. Okay. So basically, at the high level, we can build some statistical learning theory to argue that if we see the number of samples in the training phase is of the order, the intrinsic dimension, learning theoretic dimension of this family of algorithms over epsilon squared, that's sufficient to get uniform convergence, and then that means you kind of epsilon generalize. And so now, what is this notion of dimension? Learning theoretic notion of dimension at a very high level, and then I'm going to give you the proper definition. It measures the ability of the functions in this function class. So the notion of dimension. So I'm going to use pseudo-dimension of a family of utility function. Intuitively speaking, pseudo-dimension, this notion of pseudo-dimension is trying to capture the ability of the function in my function class to fit complex patterns. Because the more complex patterns I can fit, the more samples I need to generalize. That's very high level speaking. Now, actually, I want to tell you first what our result is, and then I'm going to define VC dimension, pseudo-dimension, and then hopefully everyone is going to follow along. So, but for now, we're going to rely on these tools from statistical learning theory that tells us that the number of samples to generalize is of this order, dimension of the function class at hand over epsilon squared. And so, like our main contribution in this line of work, one of our main contributions in this line of work is to give a general theorem for analyzing these notions, the pseudo-dimension, the learning theoretic notion of dimension via dual function classes. So this is motivated by this data-driven algorithm design. So if I have a family of utility functions that come from data-driven algorithm design, like this family U alpha utility functions for algorithms parameterized by alpha, then we show that to analyze this notion of pseudo-dimension, it suffices to take advantage of the structure of the dual function class. And so what is the function in the primal function class here? So for any algorithm A alpha, I have utility function U alpha, right? These functions in the primal function class take as input, they are parameterized by alpha, the parameter of an algorithm, and take as input instances of the problem. Yeah, these are my primal functions, the functions of my primal function class. And that we show we can give a bound on the pseudo-dimension of this function, the family of functions from this primal function class, as a function of how structured the dual functions are. And what are the functions the dual? A function the dual now is parameterized by an instance of the problem and takes as input hyperparameters, so parameters, algorithms parameters. Okay, and what we're able to show is that if these dual functions are piecewise structured, then we can give you a bound on the pseudo-dimension of the original primal function class. Okay, this is at a high level speaking what our result was. And one of our general results in this line of work is, so we give a bound on the original function class that we really care about, utility functions induced by algorithms family, as a function of the niceness of the dual function class. And you might wonder, why did we write this theorem? Well, because we first looked at many case studies. And so over and over again in these case studies, for example, in the knapsack problem that I mentioned to you earlier, turns out that you can argue, and this was actually already a problem, as I mentioned, already studied by Barish Gupta and Team Ravgarden. So for the knapsack problem, for the family of algorithms that I told you about, turns out that actually if you fix an instance of the problem, vary the hyperparameters, the utility function is a piecewise constant function with not too many pieces. We'll have like a big O and square pieces. And each of these discontinuities roughly corresponds to a moment when you prefer to add one item in the knapsack to another one for some value of some parameter alpha. Okay, so this was true that for this knapsack family of algorithms, the dual functions are piecewise constant. It was also true in other applications that we considered in our work, because we looked at several of them. So for example, here's an example of an application, like an example of a case study that we looked at. It's trying to learn how to cluster items, right? So here, a natural family of algorithms that people use all the time in practice and we teach all the time in undergraduate machine learning algorithms are like linkage-based algorithms followed by dynamic programming. So, right, so what we do, we start with each point in its own little cluster, And then in step 1, we somehow link all the items into a hierarchy by repeatedly merging the 2 closest clusters. Okay, this is step 1, very efficient. And then in step 2, you do dynamic programming to find the best pruning according to your performance measure from this hierarchy. And again, once you have a tree, step 2 is also fast. So by design, these are polynomial time algorithms. Now, the performance in the end, say here your performance is the quality of the clustering that you output. The performance of this algorithm depends a lot on how you do step 1, because you can have multiple choices for doing step 1. What do I mean? I start with each point in its own little cluster, and then I repeatedly merge the 2 closest clusters. There are many notions of closest, the distance between clusters you might consider. And so, for example, single linkage defines the closest clusters to be the distance between 2 clusters to be the minimum distance between points in the corresponding clusters. Complete linkage defines the distance between 2 clusters to be the maximum distance between points in the corresponding clusters. And you can easily see that you can output down infinite parametric families of linkage procedures that, for example, interpolate between single linkage and complete linkage. Right? And so in this series of papers called 2017 and I created 2020, we looked at such family, large parametric family of algorithms, and we talked about how many samples do we need to learn a good clustering algorithm. And again, in the proof, even there again, turns out that the key result that we used, what we needed in order to prove the abound and the pseudo-dimension of the family of algorithms that we care about, was this structured result where we show that if we fix an instance of the problem and vary the parameters of the family of clustering procedures, our utility function, the quality of the clustering, is a piecewise constant function again. Okay, so in the knapsack problem, this appeared. For clustering problem, this appeared. It appeared in many other cases. So for example, I'm not going to go through them in details. For example, we also looked at more econ problems like pricing problems. Maybe you're trying to price items to maximize revenue, and the family of algorithms you consider are posted prices. So you set a price per item, and you let each customers come in arbitrary order, and they buy what they want at the current prices. Yeah, that's a very concrete family of algorithms. Turns out that again, you can prove that if I fix an instance of the problem, and they vary the parameters in this case, which are the prices on the items, the loss function is piecewise linear. Now, of course, this will be a high-dimensional situation, right? Because I have many items, a price for each item. But again, you can prove that the loss function, the utility function, is piecewise linear. And the same thing happened over and over again. That's why at some point I decided to have to write a general theorem so it can decouple basically the structure result of the problem from the statistical aspects of the problem. Okay, and this was really the intuition behind that general result that I mentioned to you. This is the intuition behind this theorem. Just the fact that this structure appeared over and over, and I thought it was good to have this general result that again decouples the structure of the algorithmic problem from the statistical aspect. Okay, and now to define what these results are, because from the questions I get, I'm just going to tell you a little bit more so that you get an idea about what I mean by these notions of dimensions, because from the questions I see that some people have never seen them. So first of all, if we deal with binary valued function classes, like in classification, right, supervised classification, you're trying to classify cats versus dogs, for example, right? The learning theoretic notion of dimension that appears is VC dimension. And so what is the VC dimension of a function class H? Is the cardinality of the largest set S that can be shattered. Or in other words, is the cardinality of the largest set S that can be labeled in all possible ways by functions in my function class H. Okay, this is what the VC dimension is. And this is the notion that appears in all those famous sample complexity bounds. It's the cardinality of the largest set of points that can be labeled in all possible ways by functions in my function class. So for example, VC dimension of linear separators in R2 in the plane is 3 because there exists a set of free items that I can label in all possible ways with linear separators. But you can argue that for you can argue that no matter what set of 4 points you put down, there will be a labeling of these 4 points of linear separators that a labeling of those points that cannot be achieved with linear separators. Okay, so no set of 4 points can be labeled in all possible ways with linear separators in the plane. Okay, so that's why VC dimension is 3 for linear separators in the plane. In general, it's D+1. But this is just so that we can get used of what notion of dimension is. For us, we really care about real valued function classes. And so the notion that we analyze in our work is a pseudo-dimension, which what is a pseudo-dimension of a function class F is the cardinality of the largest set S that can now be shattered in a real value sense. And so what does it mean is the cardinality of the largest set S of points x1, x2, xm, and now I also have thresholds y1, y2, ym, such that all above, below patterns on my m points with respect to these thresholds can be achieved by functions in my function class. So for example, if I have m equals 2, then there should exist a function f1 that achieves the below pattern. So I should have f1 of x1 is smaller than y1 and f1 of x2 is smaller than y2. I should have a function f2 that achieves the above below pattern, a function f3 that achieves the below above pattern, and a function f4 that achieves the above pattern. Okay, and if you've never seen this, actually, just as a side note, actually turns out that the pseudo dimension of a function class f is just the VC dimension, a very natural, of a related below the graph function class. So my function class f is not a class of binary valued functions. You can define a related function class that is a class of binary functions induced by this, the below the graph function. And really what pseudo dimension of f is the VC dimension of this below the graph function class. Okay, but in our proof we really use a definition, this definition here. So that's why I mentioned this one. So the cardinality of the largest set of points that can be shattered in a real valued sense. Okay, and now with this, as I mentioned, this pseudo-dimension comes once this pseudo-dimension notion comes in this uniform convergence bound that I was describing earlier. So in order to talk about how many samples do I need to generalize, it suffices to understand the notion of pseudo-dimension for my family for my function class of interest. And again, so going back, I can now describe this theorem in a bit more detail. So this is from joint work with a couple of my former students, Ellen Bittersik and Travis Dick, and also Dan de Blasio, Carl Kingsford, and Thomas Sandholm from CMU. So here's what the theorem says more precisely. So we really want to analyze a pseudo-dimension of the family of functions, utility functions induced by our family of algorithms, right? We have a parametric family of algorithms parameterized by a parameter alpha. For each parameter, I have a utility function u alpha of I, and I really want to analyze the pseudo-dimension, the learning theoretic notion of pseudo-dimension for this family of utility functions induced by my algorithms. And so what we are able to show is that if the function is a dual function class, and so this is what the functions the dual function class are, I now fix an instance of the problem and vary the parameters, right? So I show that if the functions the dual function class are piecewise structured in the sense that if I fix an instance of the problem and I'm thinking the corresponding dual function ui, where I vary the parameter alpha, turns out that I can partition so if I can partition the hyperparameter space, so the parameter space of some nice boundary functions coming from a function class f, so I put down these nice dotted boundary functions in the parameter space, such that inside each of the piece given by this boundary, so maybe inside this piece, for example, the loss function, the utility function ui of alpha comes from another function class g that is also nice, right? So if these dual functions are the kind of piecewise structured, then turns out that I can give a bound on the pseudo-dimension of the primal function class as a function of the niceness of these dual functions. So I can give a bound on the pseudo-dimension, the learning theoretic notion of dimension of this primal function class as a function of how nice these boundary functions are and how nice these functions inside the piece are. Right? So for example, for item pricing, I mentioned earlier, these duals are piecewise linear, right? Or for the knapsack problem, when alpha was just one dimension, like the parameter was one dimensional, and we had piecewise constant functions. But more generally, this can be, like in many of the other case studies, there are more general boundary functions, more general functions inside the piece, and so that's why this abstraction encapsulates all of those. Okay, how well am I doing on time? Because I also want to mention going back to learning machine learning algorithms. Okay, cool. So then I'm not going to go through the proof here because I have a proof sketch. If you're curious, come and talk to me offline. I'm just going to mention one insight in the proof. So it turns out, like, what are these dual functions coming into play? So for those of you that have seen learning theory before, so if we fix endpoints, there is something called Sauer's lemma, where we can bind the number of labelings of these points with function from a function class as a function of the BC dimension of the functions in F. Now, where are the duals coming into place? Like if I have now a number of functions that I put down, like these are my boundary functions, and you can ask how many of these pieces do they induce? Because now this will be relevant when you count the number of sign patterns in the final pseudo-dimension bounds, right? Turns out that you can bound, if we have m boundary functions and you want to bound the number of regions induced, you can kind of use the Sauer's lemma on the dual function class. this is where these duals appear in the proof itself. Okay, but I'm going to skip this because I want to tell you also about going back to machine learning. And there is also a cool proof sketch. You can come and talk to me offline if you're curious to actually see the proof sketch. In the end, it's just counting and using the two key facts that I told you about the structure of the Bauer-Saurus lemma on the primal and the dual. Okay, but going back, so what's exciting now, there is this general theorem, right, where you give a bound on the learning theoretic notion of dimension of algorithms, families, right? And turns out that this theorem can be applied to a variety of situations. So here are examples. So I mentioned we already had examples in mechanism design and econ, but they're also like in operations research, for example, people solve mixed integer programs using branch and bound technique. And turns out you can, again, learn how to branch, learn how to bound, learn how to cut. And very cool, some of these results just apply there as well. Or, actually even theory of computing, I see some theory of computing people here, like even things like max cut, you do semi-definite relaxation followed by rounding. Well, you can parameterize the rounding, you can learn how to round. This is another example that we had in some of in our very first paper. So it turns out that such techniques can be applied in many different scenarios. And I think that's very cool. Okay, and because I only have 5 minutes, in case you are curious, you might ask, well, have you tried to see if it is really useful to learn algorithms? And the answer is yes. It's already known from prior literature, but my students also did experiments. Turns out that it's really important to learn algorithms for your type of instances. You can do much better than staying with worst case heuristics. Yes, and so far I only done distributional learning to answer some path question earlier in online learning, because you're asking, can we reduce the problem of online algorithm selection to classic online learning? Well, the difficulty is our loss functions have, if you fix instance the problem vary the hyperparameters, they have many sharp transition boundaries potentially, as we've seen already. And so we cannot use classic learning, online learning theory. And in fact, in the worst case, you might not even be able to achieve no regrets. You can show that if you have even threshold function on the real line, no regret is not possible. And so, but turns out we have some identify sufficient condition where no regret is possible. In particular, if your boundaries, so you can have sharp transition boundaries as long as you can make sure that they are not too concentrated. So if you satisfy something called dispersion. So if I look in hindsight, not too many of my boundary functions, not too many of my utility functions have sharp transition boundary in any small ball. Okay? And so we had a series of work giving sufficient condition or no regret is not possible. In the end, actually, once you have a dispersion, sufficient condition, you can use a continuous version of the classic multiplicative weights. So you can rely on it, but you have to analyze, and the difficulties are the sharp transition boundaries. Okay, cool. So to summarize this part of the talk, because I really want to go back a little bit to machine learning. So, I think, I think data-driven algorithm design, I guess when I think about data-driven algorithm design, 2 key questions that I think about are, well, what are interesting tunable family of algorithms? That's the first question, of course. And then the second question is, how do you tune these algorithms to achieve best performance for a given domain of provable guarantees? And we've already seen a little bit of distributional learning formalization. There is also an online learning formalization, as I mentioned. Okay, so I really want to make sure that I have a few minutes for machine learning as well. Go back to machine learning. So, because as Jeremy pointed out, I used to do machine learning before machine learning is popular, so I love machine learning in addition to algorithm design. So, like if you go back to machine learning, so who designs good machine learning algorithms? Right, and in particular, many machine learning algorithms, they have hyperparameters, right? And who tunes those hyperparameters? Well, these days, to be honest, graduate students, which is very boring, right? And so, or engineers, the big tech companies, right? And it's very, it's very intensive process, both in terms of human effort and compute effort. And so the question is, can we do that in a more principled manner, right? So can we talk about tuning hyperparameters of machine learning algorithms with provable guarantees that hopefully lead to more efficient techniques for tuning hyperparameters of machine learning algorithms? And this is something we've been thinking about in recent years. So this is a more recent line of work, but for example, just to mention, turns out that, for example, we had a work with my former student, Dravi Sharma, where we were talking about learning a graph for graph-based semi-supervised learning, even for the very basic regression, which is like one of the basic problems in statistics and machine learning. How do you regularize your regression? Should you use L1 regularization? Should you use L2 regularization? Should you combine the two? What should be the linear combination of the two? Right? So that's our key questions, and so we had a series of papers looking at this. And so, Yeah, so these are very, very important questions and non-trivial questions. And actually what I want to tell you about is just maybe to give you a little bit of an insight behind a recent work on decision tree learning. Because it's a little bit closer to some of the things I talked about. And of course, you can also talk about hyperparameter tuning in neural networks. So I want to spend like 5 more minutes or 3 more minutes for talking about how do you learn how to build decision trees. Okay, and so what are decision trees? So this is this is from a very recent work of my now former student Ravi Sharma, for which he got the outstanding student paper at UAI, a major AI conference. Okay, so what are decision trees? You know, these are very basic machine learning techniques that are still used today in situations where you care about interpretability, right? And so what is a decision tree? Each internal node, so we are thinking about classification problems or maybe regression, let's say stay with classification. So what's a decision tree? It's a tree that looks like this. Each internal node corresponds to a split based on a node splitting rule. And then, for example, a test on a feature, and then each leaf node corresponds to predicting a single class. So here, for example, is an example of a decision tree for deciding whether to screen or not screen somebody for lung cancer. Okay, now it's known from classic, I guess it's known from classic work in machine learning theory, but if I'm given a data set and if I'm able to find the small decision trees, if one exists, then you get generalization immediately. Now, unfortunately, the algorithmic problem of please give me a small decision tree for this data set if one exists, even if I promise you that one exists, that's MP hard is known from the 70s by Ron Rivers, but even recent work shows in Colt and Fox show is also there are super constant in approximability results under stronger complexity assumptions. So the underlying algorithmic problem is hard. What do people do in practice? Well, they do top-down heuristics. So like where they do one of the techniques, among others, but the most prominent one that I teach in basic machine learning is top-down heuristics, where these are greedy approaches where you grow a decision tree in a top-down fashion from the root to the leaves by repeatedly replacing an existing leaf with an internal node based on a splitting criteria. And now it turns out, as you'd expect by now, empirically, different criteria work best on different data. Right? And so examples of classic criteria are entropy criterion, Gini impurity, Kernzen-Mansour criterion, and in fact, popular implementations, even like Skit, leaves a choice of splitting criteria to the user. So there is no magic splitting criteria that works everywhere. So it makes a lot of sense to try to learn how to build decision trees. So via these top-down procedures. And so this is exactly what we've done in this UI paper. We introduced a parametric family of splitting criteria that basically incorporates the known, the ones widely used in practice splitting criteria. Okay, and then we show how we can tune the splitting criterion based on past training examples using not too many problem instances, past problem instances. So basically, we give a sample complexity of how many problem instances do we need to learn how to build decision trees. And without going into the details, turns out that actually in the analysis, we end up using this dual function classes that I told you. So it suffices to fix an instance of the problem, vary the parameters, you get a piecewise structure. Then perfect. We can just apply in the general, plug into the general theorem I told you about. So the same thing appears there as well. Okay, and this is my last technical slide. Now, of course, decision trees are still used these days, especially if you care about interpretability, but everybody wants to use neural networks, we all know, in the past decade. So can we say something interesting about neural networks? It's a problem that I've been thinking about a lot for several years, and now we have some interesting recent result where I'm able to say something interesting. Now, the difficulty, without going into details, the difficulty when you talk about neural networks is the following. So even if I learn the hyperparameter of my machine, or my, say, network structure, because when I do neural network, I can talk about the hyperparameter of the network, the architecture. Even if I learn the hyperparameter of the architecture, the difficulty is that on a new instance of the problem, on a new data set, I have to do an additional optimization. I need to find the best weights that give me the best utility function. And because of that, this is the underlying mathematical structure is much harder compared to, let's say, learning decision trees or some of the problems that I told you earlier. But but we have some very exciting recent results where we're able to say something finally interesting in the case where now if I fix an instance of the problem, what we call the parameter-dependent dual function is piecewise structure. So if I fix an instance of the problem, vary both the hyperparameters and the weights of my network, if this is piecewise structured, say piecewise polynomial, then we're able to show that actually the true utility function that you care about if you fix an instance of the problem and vary very just the hyperparameter, but so basically we already take a soup of the weights, the best possible weights. We're able to show that if it's parameter-dependent dual is piecewise structure, then the actual dual that we really care about when we talk about learning theoretic notion of complexity, this is structured. Okay, and I'm going to stop here, maybe just go at a high level. So first of all, so going back to the higher level, so I think data-driven algorithm can overcome major shortcomings of classic algorithm design by adapting the algorithm to the domains at hand. And this is very natural because, in practice, people already are using this because different methods work better in different settings. We have a lot of past training instances, so it makes a lot of sense to try to learn an algorithm that does well on our type of instances rather than worrying about worst-case instances. So I think the problem is well-motivated. People already do this all the time in practice, and so but I also think it's very important to also have provable guarantees for these data-driven algorithms, and this is exactly what the work in my group has been doing over the past few years to come up with, to lay theoretical foundations for data-driven algorithm design. And we have some cool general principles, but also many case studies. And this expands, as I discussed, both the frontiers of algorithm design, but also of machine learning itself. Because we can start talking, first of all, from a technical point of view, learn more complex objects. We are learning algorithms, but also we can, so that's technically very interesting, but it turns out also, as I mentioned, machine learning algorithms themselves have hyperparameters, so we can talk about learning machine learning algorithms as well. Okay, so definitely expands the frontiers of machine learning as well. Yeah, and so I guess I can stop here, maybe just mention a couple of just open directions. So this also relates to some of the questions that I've got earlier. So like right now we have very general bounds, but as I mentioned earlier, those bounds apply no matter what the underlying distribution of a problem instances is. That's their beauty. They apply no matter what. But of course, if your data is even nicer, like if you mentioned, if you have bounded variance or some other properties, maybe our bounds are loose. So a very natural question is, can we get tighter data-dependent bounds? And there are tools in learning theory to do so. And for some cases, we've done them, but nothing too general. For like some pricing problems, we've done them, but only for very specific cases. So, but I think the question is wide open here, especially in getting some general principles that apply more broadly. And that's one direction. Another direction is obviously thinking about other learning models. So we model the problem of data-driven algorithm design as a statistical learning or online learning. But of course, you can hope to try to use reinforcement learning or maybe LLMs, like one of the students that was on many of the LM-Vitersik, she was my student, now Professor Stanford, she was on these beautiful theoretical results that I mentioned earlier, the dual function classes and so on. She just posted recently a paper with some of her students where she was trying to use LLMs to learn algorithms. But of course, no provable guarantees yet. So it would be wonderful if we, elevate that and try to also have some provable guarantees. And maybe long term, by interactive, I guess, by using this approach, data-driven algorithm design, the human, I guess, AI in the loop, maybe we can get algorithmic paradigms as well as proof techniques so that the humans are not even able to think about before.
We had a few questions along the way, but we have time for a couple of questions.
Could you comment on any links with program synthesis as a sort of paradigm to also learn algorithms, somewhat from data, especially for program synthesis through examples, if that's something that has come up in these kind of classes?
So it's a great question. I guess, to be honest, I have not followed the literature very closely, but at the time when I was looking at it, I think we're maybe using more like learning, it's more query-based learning. So this is, I guess, maybe I can add it to open questions. So maybe I should have done it to, I'll add it to my open questions here. I should have added here, connect to other tools like membership query learning. I should have added here. And that's, I think, more connected to program synthesis, because there is also membership query where you can pick your own maybe type of examples and then see, you get feedback somehow about that, maybe from a human. So, but yeah, I agree, it's a generally related conceptually. I don't know of any technical relationship yet.
Thank you.
Yeah.
So if you drop the assumption of IID inputs,
yes.
Is the problem, can you prove lower bounds saying algorithm design is impossible in this way or something like that with no regret? If you have an adversarial...
Yeah. In fact, we've proven that. Yeah. So because we have piecewise, we have lower bounds. We had the Fox 2018 paper about that. And so, like even for knapsack, even for a lot of these problems I talked about, yeah, you can definitely prove lower bound. So in fact, because the loss functions will have sharp transition boundaries, and you can get a worst case sequence of instances or distribution of worst case sequence of instances, so that those sharp transition boundaries will concentrate, and so no regret is not possible. The way we overcome it, again, like if the loss functions don't have concentrated discontinuities or sharp transition boundaries, then no regret is possible. And you might ask, only does it happen in the real world? Concretely, to show this that, well, if the input instances are already smooth, so for knapsack or for clustering, if I take maybe the arbitrary to start with, but then maybe we add a little bit of randomness, like in the smooth analysis model, then we can show provably that the corresponding loss functions will have dispersed boundaries. And so we are able to show this. But you're right, in the worst case, on online learning, no regret is not possible. And dispersion is a sufficient condition. It would be interesting to find other conditions.
We do one last question before we take over there, and then
I'm curious about how you search the parameter space in practice. So it looked like for maybe some of the discontinuities or flat regions. So maybe optimization is hard.
Yeah, it's a good question. So I didn't tell you exactly. So I mentioned very, very early on here, like so I didn't tell you exactly how do we find, so I told you about the statistical aspect. So can we even, like as a question that I addressed today, can we even in principle learn algorithms, right? Can we generalize from past instances? But I didn't tell you, well, if I give a training set of instances, how do you find the best algorithm over the training set of typical instances? That's a different algorithmic problem, the classic algorithmic problems. And so we have some results. It's again also a widely open question. I was trying to see if I have it here somewhere on my slides. But it's again a widely open question. We are able to say some interesting results for things like clustering when you have a small number of parameters. So like, because we have something called the execution tree, we had an iClear paper, we had efficient algorithms. So to answer your question, basically, that's finding the best algorithm of the past over the training set of typical instances is a non-trivial question, like how do you do that in an efficient manner, computationally efficient manner. We have some results for when you have small number of dimensions, like clustering 1 or 2 parameters for your algorithms families. And even there to get something that is actually runnable in practice. Oh, I think I showed you those experiments. I think I did have a slide with the experiments. To even show, like I flashed them by, to even show that slide with the experiments, if I go back to here, I guess I have to do a slideshow again. Yeah, so to even run these experiments in practice, right, to compete with the best way, to learn the best way to link, for example, we had to use some interesting tricks, like something called the execution tree, right, so where we're able to, right, to find the best, yeah, so I guess in principle for clustering, if you are just trying to learn to interpolate between single and complete linkage, for example, there is a polynomial time algorithm that our process suggests. It's the loss function is, so if I pick the problem and vary the parameters of the linkage algorithm, I get a piecewise structure with the most n to the 8 pieces, or n is the number of input items, objects that I want to cluster. So that implies a polynomial time algorithm, because if I'm given m instances, for each of them I find the corresponding piecewise structure, m times n to the 8 discontinuities, and I find the best interval. But that's not runnable. Like I wouldn't have been able to get large-scale experiments based on that. And so, like for example, we have some in this iClear paper. The key contribution was to come up with a more efficient algorithm that, like m times n to the 8 is the worst case number of discontinuities. In the real world, this is much smaller, maybe linear. And so we have what we call output-sensitive algorithms, where the runtime depends on the actual number of discontinuities that appear on your instances. And so we're able to get this for certain problems like learning to link. But in general, it's a cool unanswered question.
Let's thank Nina again. Like 20 minutes to do the lead tutorial.